Okay, so let's continue our discussion on quotient groups. So in the previous lecture, we had discussed the fact that if there is a homomorphism phi from a group G to a group H, so it's a group homomorphism. So it's a group homomorphism. Then what we do is that we choose an element A out of H, and we consider the fiber of A. So what is the fiber of A? So fiber of A is this set. Okay. So we choose the fiber of A in G. So suppose this is G. So we choose the fiber of A. Okay. So in a way, the fiber of an element is the set in G which projects to A in H. Um, these fibers partition G, and if I name this fiber to be say chi A, then we have discussed the fact that the collection of all these fibers, it come out to be a group, and we call this group the quotient group. So let me, we had also discussed several examples. Let me start to this lecture with the following definition, and this definition is what basically summarizes the previous lecture. So let phi from G to H be a group homomorphism, with kernel K, with kernel K. The quotient group, or factor group, which is G mod K, is a group whose elements are the fibers of phi with the group action, I should say the group operation. So chi of A dot chi of B is equals to chi of A. And how we had expressed this group action is, we said that if you take any fiber chi A, you project it back to the set H, so it gets projected to the point A. So suppose you have two fibers in this form, then the composition of A and B in H is say AB. Okay, then you bring AB back to G, the fiber of AB, so it's chi of AB. So in a way, composing chi A and chi B gives you chi AB. That what we basically do is that we project them to the set H, we compose the elements, and then we bring back the fiber of that composed element. So this is the way in which we had defined. So this is the way in which we had defined the concept. Okay. Now we haven't much used the concept of kernel yet of now, but we will now see how this kernel is important. Okay. Like the way we had discussed the previous lecture, there we had no need of this kernel. Okay. In this lecture, we will be requiring it. So let us continue. So in the previous lecture, I had just stated this fact that we had discussed an example regarding the set of integers. In that lecture, we had seen that the kernel of the homomorphism seems to be a single element in the factor group, and every other element seems to be some sort of a translation of this kernel. So we are going to emphasize on that fact in this lecture, which will eventually justify the term quotient in the concept of quotient groups. Okay. So for that we need the following proposition. Let phi from G to H be a group homomorphism. Okay, be a group homomorphism. Um, let's say its kernel is K. Its kernel K. Let x be, or I shouldn't do that, let chi be an element of G mod k. Okay, so let this be the fiber. Let us denote it as a fiber, be the fiber of some element A, obviously in H. Clear? Then we have the following observation. Then number one, that any element you choose out of chi can be written as uk such that k is in the kernel. Similarly, for all elements u in chi can also be expressed as the set ku such that k is in the kernel. Okay, is it clear? Let's come to the proof of it. Proof. Let me consider a bit lighter shade. Do I have? Yeah, I have it. Okay. So how does the proof go? So we have, equality of sets. So the obvious procedure we would follow is a both-sided inclusion, right? Let us check it out like that. What we do is that we define this set first. So let uk be defined as the collection of elements of the form u small k such that small k's are elements of capital K. Okay, we will prove one, and all the steps will be analogous in the proof of two. Okay, so what we need to show is that for all u in chi exactly equals this set, right? Okay, so let us first choose. Okay, let's start with an element from uk. Okay, so how do we do this? Okay, so any element of uk is of this form. Then what is phi of uk? So phi of uk is so it's phi of u, phi of k by homomorphism, but phi of k is 1 because k is the kernel. So it's simply phi of u. Okay, we are talking about elements. U's are elements from x, so phi of u is equals to a, right? Okay, let me just structure it out a bit. So let u be an element from chi. Consider the element uk from the set u capital K. Okay, so I start with an element u small k from u capital K and eventually reach the point that the image of uk under phi is a. So that means uk is in the fiber of a, but the fiber of a is exactly right. So obviously this was an arbitrary element from u capital K, therefore u capital K is a subset of right. Clear? Okay, now we need to show the reverse inclusion. So let let G be an element from chi. To show that G is an element of UK, how do we show this? Let K be the element U inverse G. U is an element of chi. Okay, U is an element of chi. U is an arbitrary element of chi. Then what is phi of K? Phi of K is phi of U inverse, phi of G. Phi of U inverse is phi of U whole inverse, phi of G. So yeah, this is A inverse. This is A. So it's 1. Therefore, K is an element of, therefore, K is an element of capital K. But that now K is in the form U inverse G. Right? K is in the form U inverse G. So that implies G is in the form UK. But K is an element of capital K. So this implies this is an element of U capital K. G was an arbitrary element from chi, right? That implies chi is contained in U capital K. Thus, U capital K is equals to chi. What does this statement eventually tells you? 2 is analogous to 1. Right? You just need to change the notation, nothing else. You just need to define the set KU. You just need to define the set KU as K small u such that each K is in capital K. Yeah, that will do. Just that is what you require. But what does it tell you about the fibers? Therefore, now chi was an arbitrary element from the from the set of all fibers, right? From the group of all fibers. Therefore, G I should write it as every element of G mod K So this is just the notation I have used to, now this notation was by far not as defined as it is now, right? Let me just explain you what I try to do out here. See, so what I actually proved here is that if I consider the set of all fibers of of psi from G to H, which is obviously a group homomorphism. I am not stating that again. With kernel K, then every fiber, of phi is some translation of K. Translation of K. This word, is more justified if I use the additive notation, right? So in additive notation, UK is of the form U plus K. It seems more like what we call a translation. Okay, so just consider that to be a translation with the multiplication notation as well. Okay, in a way, it's just a multiple of the set key, right? It's just scaling the set key. You can consider the word translation, or you can also consider the word as the as some scaling of key. Okay, but in a way, it's some multiple of key or some extension by translation of K, and the element K. So K indeed acts as an element itself. So the element K is 1 dot K in a way, right? What is this? This is the set of elements which gets projected to 1, nothing else. K is the fiber of 1. If you carefully observe, any element you choose out of K, it is projected to 1. So K, the kernel of the homomorphism, is basically the fiber of 1. It behaves like a single element in the set of all fibers. That's quite obvious. Every other element in the set of all fibers behaves as a translation of K, right? So in a way, if I start with a group G and I define a homomorphism from G to some group H, I get the kernel of phi. So the collection of all fibers is sort of dividing out the whole set G by K, right? So like so if I choose any element, then I say that it's some multiple of B. So this is the form which you can relate here. If I choose any fiber out of the set of all fibers, then it is in the form of some multiple of the kernel K. Now you're getting my point? So if I choose any element out of G mod K, if I choose out, so this is the notation we will now be using to denote the set of all fibers of phi under this where phi is a group homomorphism. So if I choose out any element from G mod K, then it's in this form, where U is an arbitrary element of G mod K. Okay, rather U is an arbitrary element from chi to be precise, right? Are you getting my point? If you go back to this theorem, what is this theorem saying? That for all U in chi is equals to UK. So U is an element from chi, U is an arbitrary element from chi. But any element you choose out of G mod K is in this form, which is quite related to the division of integers, right? What does this K usually is called? It's called the quotient, right? So every fiber of phi, or rather every element of G mod K, is in the form of some quotient when the fiber is divided by K. That's the sort of you know psychology we have used in giving this term. So that's why we call G mod K a quotient group. So it's in a way we are dividing the elements of G by K, quotient group. Clear? Okay. Now obviously we have seen the fact that every time when we discuss quotient groups, it's not always that easy to talk about fibers. But now we have seen that any fiber you choose, you can always consider it to be in the form U times capital K, where K is the kernel of a group homomorphism and U is an arbitrary element from chi. Rather, U represents all the elements of chi. So we define sets of this sort because in a way, if chi represents the elements of G mod K, so do UK sort of elements, right? Right? So definition, yeah. let me just write it in this way. For n a subgroup of G and small g in capital G, we define Gn to be the set of all elements of the form G small n. So that small is in capital. And we define Ng. So let me use the notation for definition. So it's Ng such that n is in capital. So this is called the left coset of n in G. This is called the right coset of n in G. Okay. If you consider the group G mod K and you consider certain element of chi, then we have seen that chi is in the form U capital K, but it's also in the form K capital U. So indeed, in the group G mod K, for all U in chi, where chi is some element of G mod K, UK equals KU. Right? We will explore this more as we move on in our discussion. Okay. Elements in the coset are usually called the representatives of the coset. Okay. Why is it so? Suppose you consider two elements from the coset, or suppose you consider two cosets. Okay. Suppose you consider, if U1 is in chi, U2 is in chi, then chi is equals to U1k also equals to U2k. Right? So if you choose two elements U1 and U2 from UK, then that exactly implies that U1k must be equals to UK and U2k also must be equal to UK. So in a way U1k and U2k are also same, right? Because UK is sort of this fiber, but U is an element in chi as well. So if U1 is also inside chi, U2 is also inside chi, and chi can be represented in the form UK for all elements U in chi. So U1, so chi can also be represented as U1k, also be represented as U2k. So they must be same as sets, right? So if you choose any element from the left coset, then every element of the left coset represents the same coset, right? Any element you choose out of a left coset, it represents the same coset. That's what we exactly want to say, right? Okay. So that's why they are called the representatives. This is actually, more, I should say, this is actually, more obvious. We will get a more obvious visualization of this part when we discuss the concept of a normal subgroup. It will eventually come now. I guess it's clear, right? Okay. Clear? Okay. So if I now consider the structure of G mod K as this, collection of all left cosets. Now we have already seen the fact that if you consider a collection of all the left cosets in, or I should say the collection of all elements in the quotient group G mod K, then the left cosets and the right cosets are sort of identical. So we can all just term them as cosets, right? So if I consider two cosets, say GK and HK out of the quotient group G mod K, then recall how we had defined the the operation of the fiber. So we have defined that chi A chi B is equals to chi AB, right? Right? So if chi A dot chi B equal to chi AB, where A and B, where chi A is the fiber over A, chi B is the fiber over B, and chi AB is the fiber over AB, you can relate this to here, that GK actually represents the fiber over, the element. So it's indeed, you can call it as some chi A, you can call it as some chi B. G is the element of chi A, so G maps to A. H is the element of chi B, so H maps to B. So if we compose them out, we will get a composition of G and H indeed when you bring it back, right? Because these two composed will give you chi AB. So elements GH will be in the fiber over AB, right? So GH will be here. So in a way we can compose these two together as GHK. Okay. So if I consider this operation GK dot HK to be GHK, it's a well-defined operation, and we have also already seen that this operation defines the quotient group to be a group. So indeed this gives a group structure to G mod K as well. Right? You can also check it out whether this operation is well defined or not, but I will leave it as an exercise. Okay, let us consider some examples. Let me think of some very trivial examples. Suppose phi is a group homomorphism from G to H. G and H are both groups, obviously. Let this be an isomorphism. Let this be an isomorphism. So it's an onto. It's immediately onto, and it's 1 1 as well. If it's 1 1, then the kernel of phi must be 1, right? We can also represent this as the trivial group. One, I will most of the times I will represent this trivial group as capital 1, in a sense bold 1 or whatever you call it. Okay, trivial group. Clear? So in the previous lecture we had seen that the quotient group is in 1 1 correspondence with the image of G over this homomorphism. So G mod this kernel is the trivial group. It is isomorphic to phi of G, but phi of G is G itself. Sorry, phi of G, yeah, phi of G is G. Sorry, no, it's onto, right? It's onto. Yeah, it's onto. So G is isomorphic to H in a way. Yeah, it's isomorphic to H. Or you can also consider this to be G, because G and H are isomorphic. Whatever, right? Clear? Okay. So yeah, this is one very so this indeed speaks of the fact that G mod 1 is isomorphic to G. So if the kernel is trivial, then we are talking about the group itself. The quotient group indeed is the whole group, right? What about G mod G? What about G mod G? Let me speak it out in this way. Yeah, it somewhat seems like in this. So A mod B is equals to C implies A mod C is equals to B. Some sort of this will be observed here. So sort of you can relate it to the division of integers, the quotient groups, right? If I consider phi from G to H to be the trivial homomorphism, is the trivial homomorphism. What is the trivial homomorphism? So it's the homomorphism which maps every element to the identity element. That is, phi of G is 1 for all G in capital G. Then the kernel of phi is the whole G, right? The kernel of phi is the whole G. The image of G is just 1, right? The image of G is just 1. So therefore, G mod the kernel of phi, which is G, is isomorphic to 1. Right? So it's the trivial group. Clear? Okay. So yeah, these two are pretty good examples though. Okay, now how we have defined quotient groups is that in a way we started with a homomorphism, we considered the kernel of the homomorphism, and we formed out the quotient group with respect to that kernel. But the kernel is indeed a subgroup of G, right? It's a subgroup of G. We have already proved that in some previous lecture. Now the obvious question arises that if eventually we are requiring some subgroup of G to define this quotient group, then can we do it with respect to any arbitrary subgroup of G, right? So the question is of this sort, that if G is a group, and N is any subgroup of G, then can we define the quotient group G model? Okay, that is the question. So the immediate answer to this is no, because we will eventually see it that to define the quotient group, one of the main things we require is the left cosets of n in G and the right cosets of n in G to be identical. We require this condition that Gn is equals to Ng for all G in G. We will eventually see this proposition, because if this does not hold, then the definition that then the definition Gn dot Hn, where G and H are elements from G, is equals to Ghn. This operation won't be well defined. This operation won't be well defined. Okay, clear? So let us move towards this. Okay. Or should I consider this in some other lecture? No, let's do it in this lecture itself. Okay, proposition. Let n be a subgroup of G. Then the set of all left cosets of n in G partitions G. Then the set of all left cosets of of n in G partitions G. Furthermore, for all u v in G, un is equals to vn. This actually implies that v inverse u is in n. Okay, which implies un equals to vn if and only if u and v are the representatives of the same coset. U and v are the representatives of the same coset. Okay, yeah, let's check it out. First thing first, every element of G can be written as, so suppose G is in capital G, n is a subgroup of G, so 1 is obviously in n. G can be written as G dot 1. Since 1 is in n, so G dot 1 is an element in G capital, right? Therefore, G is a union of all these Gns where G varies over the elements in capital G. Okay, so it just suffices to show that these sets, these left cosets, if they're non-empty, then they're identical. That's it, what we only need to show, right? Okay. So suppose Gn intersection say Hn is non-empty. Okay, so we choose an element out of it. Let x belongs to Gn intersection Hn, but then x can be written as G small n and can also be written as Hm, where n and m are elements from capital, right? Now, so if so x is in the form Gn and is in the form Hm, right? Okay, we need to show that Gn is identical to Hn. Okay, let me just break it down. So to show Gn is identical to Hn, we have in hand that G small n is equals to H small m, where n and m are elements from n. Okay, so we have Gn is equals to Hm. We can write then that G is equals to Hm n inverse, simply write multiplying by n inverse. Now m is an element from n. N was an element from n, so that implies n inverse is an element from n. So mn inverse is an element from n. So this is simply of the form Hn1, where n1 is equals to mn inverse. But this implies that G is in the form Hn1, which is an element from H capital N, right? So if G is an element from H capital N, if G is an element from H capital N, so this implies any element of the form G, so that implies G, uh, say GK is of the form HN1K, where K is in capital N, right? So this is an element from Gn we are starting with typically. So that implies Gk. Now this is again an element from N. So this implies Gk is in H capital N. But Gk was an arbitrary element from G capital N. So that implies G capital N is contained in H capital N. Right? Right. Therefore, we can just reverse this all these arguments symmetrically. Symmetrically, Hn will also be contained in G, which implies Hn is equals to G. Clear? Clear? Okay. What can we say about the concept of representative, that un equals to vn if and only if u and v are the representatives of the same quotient, right? Observe that if un is equals to vn, 1 is an obvious element from n, right? 1 is an obvious element from n, so this implies u is in vn, right? Similarly, and similarly, since 1 is an element of n, that implies v is in un, right? So what does this mean? This means u and v are the representatives of the same quotient. Therefore, u and v represent the same quotient, right? U and v represent the same quotient. Is it clear? So conversely, if I start up from here only, if I start up from here, that u is an element from vn and v is an element of un, then the statements are trivial. If u is an element of vn, we have seen previously what happens, right? Then un is equals to vn. You can also relate this to the standard procedure of defining quotient groups. If you know how we standardly introduce the quotient groups, we introduce them as equivalence classes. These cosets come out to be equivalence classes of the relation x minus y is in this subgroup n. So in that case, vn is sort of the equivalence class of v. So if any element is in the equivalence class of v, then that implies u is related to v. But if u is related to v, then the equivalence class of u must equal the equivalence class of v. Equivalence class of u is just un, and the equivalence class of v is just vn. So I guess now you people can relate. If you know how with respect to standard procedure we introduce the concept of a quotient group, so how these things take place, right? Okay. So this, okay, it's already a 32 minutes long lecture. Yeah. So we end this lecture here only. In the next lecture, we will be starting up with the concept that the group operation of the quotient group is only well defined if and only if a certain condition, a certain restriction is applied to this group n, which eventually leads to the concept of a normal subgroup. Okay. So meet you guys in the next lecture.